Just to show the first slide for the recording purpose, and this is one of the lecture. And let me start from the most general basic definitions which I needed to understand what happens when radiation and matter interact with each other. What are elementary processes which this interaction may include. And I just plotted these processes by simple diagrams here, and P means particle, momentum of particle, and K means wave vector of a wave. And three basic processes are shown here. For example, a particle can interact with external field or with another particle, and as a result of this interaction or as a result of some internal transition in atom, for example, molecule, this particle can produce a photon or an electromagnetic wave, and this process is called emission. Quantitatively, the emission is described by a quantity which is called emissivity. Emissivity is basically how much unit volume of given medium, given plasma, for example, can emit per unit time, per unit angle, and per unit frequency interval. So this quantity will be called emissivity, and we will deal with this quantity during this class and during the internship. So, as a result of this process, the energy of particle becomes somehow lower, smaller, and this energy comes to generate a photon which propagates out of this volume. Not surprisingly, there is a process which is exactly opposite to the emission, and it's shown here by oppositely directed arrow. When this photon interacts with particle or atom or molecule, and as a result, this matter, this substance absorbs the radiation, absorbs energy. As a result, the photon dies, and the energy of a particle system increases exactly by the amount of energy lost by radiation, lost by the photon. Absorption is a process opposite to emission, and this process is described by absorption coefficient, which tells us how much, what is the fraction of radiation will be absorbed when this radiation moves along a medium, along like unit possibly, unit 1 centimeter along the medium. So this is absorption coefficient. So there is another process when photon and particle interact with each other, but at the end, both particle and photon still exist. They can change their energy. The photon can change direction of its propagation and the energy. And this process is called scattering. In the process of scattering, properties of photon change, but the photon itself does not disappear. So these are three main processes of interaction between radiation and matter. And the easiest two are emission and absorption, and scattering is much more complicated process. It's much more difficult to include scattering in the process of radiation transfer. And in what follows, we will only be considering the two first processes, emission and absorption. We are not going to consider scattering during neither lecture nor summership. Now, what is radiation transfer? Radiation transfer is an area of science which investigates how the electromagnetic radiation is being transferred, how it's changed while propagates through a medium. So now we introduce parameters, quantities for what I introduced before, for emissivity and for absorption coefficient. So the emissivity we will call J with a lot of indices. What does indices mean? Index sigma means that there are different kinds of waves in the medium. In particular, in our case, we will be dealing with waves called ordinary waves and extraordinary waves. Ordinary waves are waves similar to those which can propagate in the vacuum. Extraordinary wave is somehow more different from the vacuum, from free space mode, and this mode is different because it may interact with generating electrons, and this interaction with generating electrons change somehow its properties. So, but this index sigma will demarcate if the given wave mode is ordinary or extraordinary. Then N is unit vector along wave propagation, and it tells us that emissivity can depend on direction of the wave propagation. Index omega, it's frequency of the wave, and it tells us that emissivity depends on frequency in general case. And then it also depends on R and T. R is location in space, which means that emissivity changes from point to point, from volume to volume. And in general case, it also depends on T, which means that emissivity is time dependent. So this is mainly a parameter of which this emissivity may depend. In similar way, there is kappa is absorption coefficient, which in general case depends on the same parameters, like sigma, N, omega, R, and T. Now, if, as I said, we do not consider scattering, and we only consider two processes of emission and absorption, it's sort of very easy to describe equation which will describe this process, the balance between emission and absorption. So the intensity of radiation in the left and its derivative over the time, so how the radiation intensity change with time is controlled by balance between emission and absorption. So the stronger the emissivity, the bigger the emission. The stronger so it enters with plus sign. Then the stronger the absorption coefficient, the bigger portion of available emission being can be absorbed. And this is why this term is proportional to emission intensity itself. So the stronger the intensity, the stronger the absolute value of absorbed emission. So this is why this term is proportional to both absorption coefficient, which is fraction of emission which can be absorbed, and emission intensity itself. Any questions so far?
No.
Okay, let's move on. The first thing, the easiest thing which can be considered is equilibrium radiation. equilibrium stationary radiation, which means that nothing changed with time or with space. This means its derivative on the left-hand side is equal to 0. And this means that combination of these two terms must be equal to 0 in the stationary equilibrium case. So it's very easy to, if you consider this right-hand side equal to 0, it's very easy to solve this equation for this value, for radiation intensity, which is down here. And here you see that this one is just radiation intensity of equilibrium radiation. It does not contain any anything about our medium, but on the left side we see emissivity and absorption coefficient, which are highly different for different media. And what is interesting, what we can conclude from this equality, that in the equilibrium case, even so, emissivity and absorption coefficient for different media are highly different. Their ratio is universal function, which does not depend on medium properties at all. So this is very interesting and fundamental property of radiation, and this is known to be called Kirchhoff's law, and there is some universal function to which this ratio of equilibrium medium always equal. And there are two important regimes when frequency of emission is low. It's so-called Rayleigh-Jeans regime of emission. You can make approximation of it and get this this form of this function. And in this case, you see in particular that equilibrium emissivity is directly proportional to temperature of the corresponding medium, and doesn't depend on any other parameters. And in our case, we will be working with radio emission, and radio emission always obeys this Rayleigh-Jeans regime. Now, what we deal with in a more realistic case. In a more realistic case, we have observer, our radio telescopes or array of radio antennas, and this array or telescope looks towards a remote source, and this remote source gives us some radiation at the source, and it also gives us something happening along the array between the source and observer, and the properties of the medium, of the plasma and the ray differ. They change with time, they change with distance, with length. And the final task is to compute what will be the emission process properties after the emission propagates through the source itself and through the path between the source and the observer. And this will be done by solution of radiation transfer equation, which I will describe in like a couple of next slides. But here I would like to just introduce a few more important quantities. If our volume, our cloud, as you like, cloud has length L, and if it has absorption coefficient kappa, where I have it? Okay, I luckily have it later. But the amount of emission which is absorbed by entire cloud can be described by optical depth. And if this optical depth is much larger than unity, this means that almost all emission incident of this cloud will be absorbed during propagation. If this optical depth is smaller than unity, then the cloud is transparent and only a minor fraction of the emission will be absorbed. And in the practical cases, you can split the cloud on small layers, and you can add up what happens in different layers and consider sequentially how much emission is absorbed in each such layer, which has only minor fraction of the entire optical depth of the cloud. And the idea is to went through all such layers and compute and add up cumulatively contribution of all these layers to understand what will be emission leaving this area and emission which we detect and record by our instruments. Now we start from sort of simplest case when we have single uniform volume. I showed magnetic field vector by these red arrows, and I just show that directions and sizes of these arrows are the same everywhere, as well as other parameters in the volume. So we consider this volume to be uniform, so nothing depends on location. And in this case, within this volume, the radiation is modified due to absorption and additional emission generated inside the volume. And there is some incident emission from the left, and this emission can be only absorbed while propagates through this volume. And as a result of some absorption of this process and additional emission and self-absorption within this volume, we get emission leaving the volume, which is in general case different from what was the incident emission. So in this case of uniform source, the general solution can be found analytically as the solution of radiation transfer. And this is based. And this portion of work about gyrosynchrotron and free processes has been completed and has been done by Ellis last summer. So this is the formula, and this is equation which describes the stationary radiation. It describes decay, exponential decay due to absorption in the volume of incident radiation of this one, while it propagates here. And this term describes how much additional emission was produced by the volume itself. So basically this one, this this factor, this combination of parameters was successfully computed and coded by Ellis last year. Let me jump aside for a while and just introduce some fundamental regimes of emission. As I said, if optical depth is large, then this term, and let's forget about this term. Let's consider this combination only. So if the optical depth is large, then this term is very small compared with unity, and this regime of emission is called optically thick. In this case, the radiation intensity is defined just by ratio of emissivity to absorption coefficient, and this combination is called source function. In the other regime, when tau is small, this combination can be expanded in a series, and in this case, the emission is optically thick. We can replace it by approximately this equation, and as a result, in the optically thin regime, the radiation intensity is proportional to emissivity and length of the source. So this is definitions which also will be needed for further work and further understanding. This is basically a repetition of what I have said right now, and I included this slide mainly for reference purpose because it will be saved in the Dropbox, so it will be available for your attention. You can refer to this slide while working on your assignments. So now let's jump to what is the most essential part of your project. So as I already mentioned, Alice already developed numeric code which describes how the emission is generated within one single uniform volume. Now the real situation is that our volume is non-uniform. And what we are going to do, we are going to approximate our real volume along our line of sight as a sequence of much smaller volumes, each of which can be treated as uniform, but each of which is different from its neighbor. So this is a standard approach for numerical quantitative consideration of radiation transfer in a general case of non-uniform media, which is like most general case. In an ideal case, for example, we could consider a huge amount of really very, very narrow layers, each of which very similar to uniform one. In practice, in most cases, we consider finite height or size of this volume element we call voxels. Each element is called voxel, and each voxel will be characterized by its own emissivity of each wave, its own absorption coefficient, all of which depend on magnetic field and other input parameters. And on top of that, each voxel can have its own height. So in general case and in realistic models, the heights of different voxels are not necessarily all the same. It can be the case, but it's not necessarily the case. So what you will be doing in your coding, you will be considering such sequence of number of voxels, and you will be considering how this your radio emission propagates through this system, and what will be the radiation leaving such line of sight. Again, each such volume is the same as this single volume. So some emission will come from left neighbor, and emission which leaves this voxel will be emission which is incident for the next right voxel. So the idea will be to carefully consider how this emission leaves one voxel and enters the other, and next one, and next one, and next one, and there will be a number of complications which in particular relates to the fact that in the plasma with magnetic field, electromagnetic emission can exist in two forms. Unfortunately, it's typo here. Let me correct the typo right away. So the radio waves in the magnetized plasma are circularly polarized, and extraordinary wave mode is polarized in a way that electric field vector rotates in the same direction as electrons generate in the magnetic field. And because the direction of rotation of the electric field and electrons are the same, this wave can interact with the plasma, with these electrons, much more closely than the other wave, which has its rotation in the opposite direction. So the wave, the electromagnetic wave whose electric vector rotates sort of coherently with electrons in the plasma, is strongly coupled with the plasma and the wave with the opposite rotation. So what will happen in real situation when you consider such line of sight? First of all, you will take a solution available from Ellis code for each voxel, and you will send it to the next voxel where parameters are different, and internal solution again can be described by Ellis solution, Ellis code. But what you will have to do, you will have to consider how this part of emission is being absorbed here and how it propagates all the way through all these voxels. In most of cases, you could consider RCP and LCP wave propagation independently from voxel to voxel. So this means that what happens in this voxel with RCP emission will only depend on what happened with RCP wave here and what are the properties of these two voxels. And this happens all the way until the radiation meets a voxel, if present, where the magnetic field is transferred to the propagation of the wave. The problem is that in the next one, the meaning of ordinary and extraordinary mode will change. And for example, if here RCP wave mode was extraordinary, here LCP wave mode will be extraordinary. Just because the transverse component of magnetic field reverted, it means that projected duration direction here will be opposite compared to this one. And such quasi-transverse propagation layers will play an important role when you will build your radiation transfer solution. And special care must be taken in such cases because depending on frequency, depending on other parameters, RCP wave or can be coupled with LCP wave either strongly or weakly, and this strong or weak coupling depends on frequency and source parameters. And you will be supposed to take special care of such cases, consider carefully, put necessary conditions in your code to make sure that you describe these coupling regions correctly. This coupling can be described by equations, which I won't show now. We will be discussing this later during summer, but right now I just want to give you general idea of what you will be supposed to do with this radiation transfer code. So these two main things which you will be doing, it's coding of interaction from one voxel to the other, to the next, and to the next, and to the next, will be the main topic of your coding, and careful consideration of quasi-transfer cases, quasi-transfer propagation cases will be particularly important in making these codes. I think I stop here and I will answer your questions. I assume that you might have some, so please go ahead and ask questions.
So the extraordinary waves are the ones that interact strongly with the matter around?
Yes, exactly.
And whether or not an RCP wave is extraordinary depends on the direction of the magnetic field.
Yeah, exactly. Yeah, you picked this very correctly, absolutely right. So basically, if magnetic field is directed to the right, I mean, at least projected component, it can be it can have any direction, but what matters is component projected on the propagation of the wave. So if magnetic field directed here to the right, then RCP waves are extraordinary and LCP are ordinary. If the magnetic field directed oppositely, then RCP is ordinary and LCP is extraordinary.
Okay.
And depending on coupling here, the wave when propagates through this layer, there are two extreme cases. For example, LCP may remain LCP, or extraordinary may remain. This is the same wave can either change or its polarization or remain the same. So these are regions of weak coupling or strong coupling.
Okay. And then the initial polarization of the wave depends on just the fields that it's passed through to that point?
Let me Could you repeat it, please, because I haven't heard you well.
What determines the polarization of the wave?
The polarization of a given wave, it can be linearly polarized, it can be circularly or elliptically polarized. And these specific properties of wave polarization are defined by properties of the medium, of the plasma, for example. In air around us, there is no preference polarization, so you can this isotropic, yes, isotropic medium. So the modes which can propagate, they can be linearly polarized or arbitrarily elliptically polarized or unpolarized. In an isotropic media like plasma or crystal, only waves with certain properties and certain polarization can propagate, and in crystals, for example, in many cases, the intrinsic polarization of waves is linear, but in so-called gyrating, in gyromedia, which in particular plasma with magnetic field, because magnetic field forces charged particles to gyrate, and this gives some gyration. And this is the basic reason that polarization state in the magnetized plasma is circular, it's circularly polarized waves or elliptically polarized waves. And the other answer on your question, what is, let's say, degree of polarization, what is proportion of extraordinary and ordinary wave modes in the total radiation flux. And this is determined by radiation source. In particular, if the radiation source is non-thermal fast electron, then you will have preferentially a little bit more, or a little bit, not a little bit, sometimes much more of extraordinary emission than ordinary emission in optically thin region. In optically thick regions, the situation can be different. Emission is weakly polarized and often polarized as ordinary wave. But the general answer is that emission, the state of polarization is determined by emission source properties and on the media where this wave. My assignment will be the following. You can scroll down and look again through this simple PowerPoint presentation with this basic essentials of the radiation transfer. And I also encourage you to Google radiation transfer, electromagnetic radiation transfer animation, and watch. If you find a video, you will find a number of simple but really instructive animations there. So this will be another way of looking at the concept.